All right, so today we're going to talk a little bit about important reactions of amines. So firstly, um, there are different types of amines. So we've reviewed this before, but there are primary amines, secondary amines, and tertiary amines. So this would be an example of a primary amine, because you can see that it is only bonded to one carbon, or the nitrogen in the group is only bonded to one carbon and 3 hydrogen atoms. So this would be a first degree or primary amine. Here we're going to show a secondary amine, which would be a nitrogen bonded to 2 hydrogens and also 2 carbon atoms. So there would be an example of a secondary amine. And finally, well, not finally, I guess we could have a tertiary amine, which would be a nitrogen bonded to 2 R groups, or 3 R groups, excuse me, and 1 hydrogen. And then we could have a quaternary amine, but these are not nearly as common as the other types of amines. So that would just mean that we had a nitrogen atom bonded to 4 different carbon atoms, and that would be a 4th degree or quaternary amine. So amines are known primarily for their basicity. So that's what they're typically used for in reactions. So to talk about some different properties of amines, primary amines have significantly, like the boiling points differ throughout amines. Primary amines actually have higher boiling points than other amines, and that's because they can form hydrogen bonds with each other, as well as they experience van der Waals dispersion forces and dipole-dipole interactions. So small amines of each type are very soluble in water. And this is mostly because each amine can form hydrogen bonds with water, including tertiary amines. So excuse me here, quaternary amines are not a thing. Amines have a gross smell, as we talked about in class. They can kind of smell like ammonia, as ammonia is an amine, but they're also known to have kind of a fishy smell. So today, now that we know some of those properties, we'll go into a couple of the most important reactions of amines that there are. So I'll go ahead and clear the screen and then we'll get started. Okay, so the first reaction we're going to talk about today is more of a group of reactions, but it's called the direct alkylation of amines, excuse me. So that just kind of signifies the addition of an alkyl group to the nitrogen, like the central nitrogen of an amine. So we'll go ahead and work through this process. So we'll just start with ammonia because it's a very common and relatively simple amine. So we have our ammonia there, or we can draw it in H. Oops, sorry. That would not be ammonia. So there we have ammonia. It's going to have a negative here. And our other reagent is going to be an alkyl halide, because that kind of makes sense in this situation. That's what we would typically use to add an alkyl group to something. So in this case, we'll have methyl iodide. And so then the first reaction that occurs is going to be an SN2 reaction. So we'll take our NH3 here, and I'm going to just redraw the methyl iodide. So there. So the electrons from the NH3 are going to substitute onto the methyl portion of that and kick off the iodine, as it is a good leaving group. That's going to result in something like this. So now we have a primary amine. So it's going to be NH3 plus I minus. And I'm not going to draw them all, but that would have 4 lone pairs. So now what happens is that we have an acid-base reaction actually. So we have formed our carbon-nitrogen bond here. So now we're going to introduce more NH3 into solution. That's supposed to be an N, sorry. All right. And then basically what's going to happen is that we're going to form something like this. So we'll have our CH3, our methyl group here, bonded to our nitrogen, which is going to become NH2. I'm just going to draw it kind of sloppily like this for time purposes. That's a 2. So we have our methyl NH2. And then in solution, we're going to have NH4I minus. Okay, so this is our primary amine now. So next, we're going to add more of that methyl iodide, so the CH3I. And that is going to leave us with a second alkylation here. So that's the thing about direct alkylation of amines, is that these reactions just tend to keep going as long as there are more opportunities to alkylate the amine. So we will see this continue all the way until we're kind of past a tertiary amine. So I'll keep going and show you what I'm talking about there. So now we'll have a CH3 here. And CH3 here. And we have a positive charge on our N, and it's coordinated to that iodide. All right, and we still have ammonia going on here. And the same process repeats exactly the same way. So I forgot to show it in this step, but basically, yeah, same thing as the first round. But now we're gonna end up with something like this, where so we'll have a CH3, NH, CH3. So that ammonia is deprotonating our N plus here in the center, which makes room for yet another alkylation when we add back that methyl iodide. So now we've gone from, primary amine all the way to tertiary amine. So we have our N plus, We got our H. Oops, sorry. That's a bad H, but you know it is. And then so we have our N plus, our I minus coordinated to it. It's our iodide. And then 3 methyl groups now. And these other 2 lines represent methyl groups as well. So then finally, we still have that NH3 in solution, and it is going to once more deprotonate our hydrogen, leaving us with, these are all methyl groups. So this interesting compound. So important to remember again, the direct alkylation of amines really doesn't stop. So it goes all the way past a tertiary amine to deprotonate that final hydrogen from the amine molecule. Okay, so this next reaction is known as the Hoffman elimination. Sometimes referred to as the Hoffman elimination of the quaternary ammonium hydroxide. So first we're going to start out here with the primary amine. And then we'll go ahead and alkylate it using the same mechanism we just talked about in the last one. That'll leave us here with a quaternary amine. Sorry about my bad hexene rings. So we'll have a nitrogen and then 4 methyl groups actually. So we'll have a positive charge on that nitrogen and a negative charge on that iodide, which is coordinated to the nitrogen. So again, I'll just show that mechanism really quickly. We will have a lone pair here. It'll attack the carbon of the methyl group, kicking off that iodide. And then that's how we did those 3 alkylations here. So once we have our quaternary amine, we proceed with an SN2 reaction. And the reagent of choice is this silver oxide. So we have AgO, 3 lone pairs on that oxygen. And here's what happens there. So we actually have, excuse me, I forgot a step. So we'll actually end up having so here's what that molecule will look like. And then it interacts with the iodide here, which will attack that silver, kicking it off of the molecule, which then leaves us with sorry, this got a little messy. So we lose a silver. This is just showing kind of the coordination of that reagent. So now we have AgO. That's real messy. And there's that oxygen has a negative charge. And then we also have an H2O molecule. In solution there. 2 lone pairs on that oxygen. So the oxygen here from the silver oxide is going to go ahead and attack our hydrogen on the water molecule, leaving us with AgOH and a hydroxide. So this isn't, we're still not involved with the quaternary amine yet. We're just kind of showing how these reagents interact to get us where we need to go. So now we have the production of AgOH. And that leaves. So now we can go back and talk about our reaction with the amine. So we have our quaternary amine here that we showed earlier. And positive charge on that N. And an OH minus here that we formed from our silver oxide earlier on. So we are going to attack the hydrogen. I don't know if it's called an alpha hydrogen when it's in relation to a nitrogen, but basically the hydrogen of the carbon closest to that nitrogen. So the OH is going to attack that, and those electrons are going to shift which ultimately kicks off that whole amine group. So then with heat, we lose an H2O because of the hydrogen that OH picked up. We also lose our whole amine there. So we're going to have N, CH3, CH3, CH3 plus, and then all we're left with after this reaction is our cyclohexene ring and a double bond here. And that's it. So that's kind of an interesting mechanism. And all it does is go from, it's the process of creating tertiary amines and alkenes. So here's our alkene product. Here's our tertiary amine product. And all of that came from this quaternary amine that we created through the alkylation of that primary amine in the first step there. And then again, our products are silver oxide, water, our reagents are silver oxide, water, and heat. And then we produce water in those two other products. All right. Okay, so in this reaction, I'd like to preface this reaction with the importance / relevance of diazonium salts. So diazonium salts are a class of compounds that are often also referred to as azo dyes. They are extremely permanent dyes due to their ability to form covalent bonds with the substrates that they are dyed with, or that they dye. And so these dyes are actually formed from amines. So we'll go ahead and talk about that mechanism. So we'll start out here with we'll start out here with the mechanism. So, excuse me. We'll keep this one pretty general so it's applicable to most things, but we'll have our hydrochloric acid and our NaNO2. We're just coordinating reagents here, so we haven't quite gotten to the real reaction yet. So we have a negative charge here, positive charge on our sodium. Okay, so then what happens is that oxygen attacks the hydrogen, kicks off the chlorine, which is a good leaving group. And now we have our H bonded to our O, bonded to our nitrogen, and double bonded to our oxygen. All right, and then it goes through with the HCl again, and this time we're also adding NaCl. Sorry about my poor handwriting. Okay. So then we're gonna have this interesting compound or this molecule here. So we've had two additions of hydrogens to that oxygen. Sorry about that. There should be an oxygen in the middle there. Oxygen is now positive because it has more than enough electrons. This half of the molecule stays about the same. We have a little bit of internal rearrangement, and we are left with something called a nitrosyl cation, which is just this nitrogen double bonded to an oxygen, and that nitrogen has a very positive charge. So next what's going to happen is that we'll take our primary amine here and our nitrosyl cation, and we've got a lone pair here, which is going to attack the nitrogen of that nitrosyl cation, which results in this compound here. It literally just adds that nitrosyl cation to the primary amine, something like this. All right, and we still have a positive charge on that nitrogen. So now we're going to treat this with chloride. Very negative charge here. Chloride's going to go ahead and attack this nitrogen of the primary amine. Which results in this guy. Just the deprotonation of that previous compound. Oops. That should only be 2 lone pairs. Okay, so then we're going to add more HCl. And this time, the oxygen of our kind of pseudo nitrosyl cation is going to attack that hydrogen, kick off our good leaving group here, which results in this situation. All right, so now we have an OH group at the end of this molecule. And once again, a positive charge on our O. And then that Cl in solution is going to take effect. very electronegative here. So our positive O, excuse me, sorry, our fluorine is going to deprotonate here. Electron movement like this. So now we've got a double bond between our nitrogens, only a single bond between our nitrogen and our oxygen. So, and then we have our hydrogen still. So no longer a positive charge there. We've reformed our acid. Which now the oxygen is going to deprotonate yet again, kicks off our chlorine. So it's a kind of a repetitive mechanism. We're just going through the same steps over and over here. But now we have still double bonded here. And we have formed a water molecule at the end of our compound, which, as we know, is a good leaving group. Positive charge on this O. So then we're going to have some internal rearrangement, movement of electrons there, and we're going to kick off our leaving group, which is the water molecule, leaving us with our diazonium salt, which is an R group, and then two nitrogens triple bonded to each other. Positive charge here, and then a Cl minus for the salt part. So again, this is how you form those diazonium salts or azo dyes, which are widely used in commercial textile industries. There has been some controversy around using these as dyes, as there has been some research indicating that they may or may not be carcinogenic. So that's something important to keep in mind. However, these dyes are incredibly permanent, so that's where a majority of their appeal comes from. I'll just wrap up with a quick little summary of why amines are so important. Let me just get this erased here. Oop, not all of it. Why are amines important? So amines they play a really important role in life itself, as they are crucial to the creation of amino acids, which, as we know, are like the building blocks of life. So without amines, we wouldn't have amino acids. And then lots of different, like we know that amino acids are important for protein function and so many different other bodily processes, but they're also important in vitamins. Amines make up a lot of, or amino acids are involved in a lot of vitamins. And then serotonin is an amine, which is, like, as we know, one of the most important neurotransmitters. They're also just kind of generally important for like cell proliferation, growth, and renewal. And they're found abundantly in protein structures, for example, in lysine chains and N-termini. So it's good to know about these different important reactions of amines.